everyone, welcome to the November session of the Royal Met Society South East Centre. And I'm going to hand over to Natalie, who is a PhD student at this university, who is talking about long-range transport of mineral dust, can a model match observations? So,
Thank you. Yeah, that was a nice introduction. They stole it from me. But yes, my PhD project is to do with coarse mineral dust. Yeah, specifically coarse mineral dust, although I know it just says mineral dust on there. But yeah, so I look at this type of thing, which is a massive dust plume coming off the Sahara. And yeah, next slide, please. Yeah, so just kind of a brief overview of what I'm going to be going over today. So I'll give you a bit of an introduction to make sure we're all on the same page about dust and why we care about it, you'll see why I care about it, and then also why the particle size is actually really important. And then I'll kind of just go through the aims of my project, what methods I've used so far, results from so far, conclusions, and then kind of talk about a bit about what's kind of coming up next for me in my project. So this picture as well, I'll kind of come back to this bit of time in the what's next section, but basically over the summer in June, for 3 weeks, I was on a little island here in Cape Verde, and I took this satellite screenshot from one day when we were just waiting for this big old dust plume to just kind of wash right over us so we could try and measure it. So yeah, this is just a brief bit about kind of the visible impacts of dust. I just like having really nice pictures. And I think these represent really well some of the important factors, not all, but some of the important ones. So for example, this was back in 2021, there was a big dust plume that came up over Europe and settled on a lot of things. So this was in the Alps in France. And you can see how obviously having that dust on the snow there really changes the albedo of the snow, and this can be important, you know, for kind of snow melt and that kind of thing. In other terms of deposition, solar panels. So I get really annoyed when people say that they can cover the Sahara in solar panels to produce, you know, unlimited power, because this is the reality. You get a lot of deposition on the panels, and actually then the maintenance costs are really high, and they can also get sandblasted and damaged by all of that kind of really powerful sand blowing. And actually just before, while I was getting ready for this, I was literally listening to an audiobook where they were talking about like, oh yeah, we could put solar panels on the Sahara, and it's grated me, and I was like, that's perfectly timed. Can also, you know, provide a lot of minerals to the ocean. I think I had a little fact on there. So yeah, there's 500 million tons of minerals added to the oceans every year from dust, which then you can produce these really nice like phytoplankton blooms, which look very pretty. There's these things called haboobs, which can hit kind of, you know, they can hit fairly populated areas. So they can travel between 20 to 60 miles an hour, quite fast. You wouldn't really want that coming at you. And then in terms of like health impacts as well, so this was a large dust intrusion from June 2020, also known as the Godzilla plume. And you can see that actually, so I think purple is like maybe the best air quality on here. Anything above that is quite poor. So you can really see how actually that was impacting a lot of South North America and Mexico. And then as well, there's this thing called valley fever, which it's only really being discovered in North America at the minute. It's to do with this bacteria that grows in the soil. And so then when that all gets blown up in little dust storms, people breathe it in, and it's really bad. I think cases between, 2000 and 2011, the infection rate of valley fever increased 800%. So quite massively. So these are kind of quite some nice visual images for you. And then again, just some more kind of things that you might remember. So this was earlier this year, the dust kind of came up and over Europe, and we saw it was really bad in Spain and France. And then even so this is London here with the Shard, even in London, we had quite a lot of dust. This was that 2020 Godzilla plume that I mentioned. It's really just a dense plume, and it was called the Godzilla plume because it basically at one point it was going all the way across to the Americas really without stopping. It was just one big big line of dust. So it was quite a significant event. And then just again pointing out that it can have quite adverse health effects as well on kind of respiratory and also cardiovascular problems. So specifically kind of on the Earth system, I guess, which is maybe what a lot of meteorologists are interested in. And actually this graphic here is specifically talking about coarse dust, but it's the same for all dust. It has very kind of broad-ranging impacts on the Earth system. So it can really impact the radiation budget of the Earth, and that's because it absorbs, it scatters radiation, and I'll kind of come back to a bit more in detail about the radiative impacts, but just know that they're there. It can also impact cloud radiative properties. So for example, like the lifetime, the reflectivity of the clouds, and also the phase of the clouds. So the dust can act as really good cloud condensation nuclei and ice nucleating particles, which means you can get rain droplets and ice crystals forming because of the kind of the injection of dust into those cloudy regions. Additionally as well, bigger particles, big coarse particles means you get more deposition because, or as in they carry more minerals. They're bigger, they're heavier, they carry more minerals in them for that kind of thing. So hopefully now you see that kind of dust is important. And now we go on to why the particle size matters. So I briefly mentioned that on the previous slide, but the particle size actually affects a lot of the subsequent processes from dust. Yeah, so as I said, it can impact the hydrological cycle, so it can impact the lifetime of clouds, and means that if you inject dust into a cloud, it could actually precipitate faster. And so that changes maybe where that precipitation is occurring. The radiative effects, I'll go into a bit more detail. Fertilization, as I said, you've got large particles, they carry more nutrients. Particle charging, this is something that I'm going to come back to again in my what's next bit, but basically larger particles tend to charge in a different direction to finer particles, which can have kind of impacts for how they're held in the atmosphere. And then kind of, I suppose most obviously is the deposition rate. So large particles, more mass, drop faster. So specifically the radiative effects, this is to do with this plot here. So so first of all, in terms of a long wave impact, so we've got outgoing long wave radiation from the Earth, and generally large particles absorb more because they're bigger, which also means that they have more to re-emit either back to the surface or to the top of the atmosphere. Whereas the finer particles, they still re-emit, but nowhere near as much. Which means that we get this kind of higher top of atmosphere warming effect, which is higher than what we previously expected. So these bars here, the blue basically represents our old understanding. We didn't think that there were that many coarse particles, or they were a bit more negligible. But then the more research we've done and the better understanding that we have of these coarse particles, we now think that actually there is that higher warming effect in the long wave caused by those coarse particles. So in terms of the short wave, they reflect less, the coarser particles. The fine particles, they're very reflective, and they reflect a lot of incoming shortwave radiation, whereas the coarse particles, they don't reflect as much, and they can actually absorb more of the shortwave radiation, and then that can be re-emitted again as long wave radiation, which again causes a warming effect. So again, we get a lower top of atmosphere cooling effect, which is what you can see here by these bars just slowly rising, which means that net effect, we used to think that dust had a nearly entirely cooling impact, which you can see by this kind of main bar here. However, now with new understanding about kind of the number of coarse particles and the impact that they can have, we're slowly thinking that there is a chance that dust could have a warming impact, a net warming impact at the top of the atmosphere. So where has this kind of new interest in coarse particles come from? So over the last, I guess it's been more than a decade now. When I was doing talks like this a year ago, it was a decade, but the first campaign was 2011. So there were these 4 campaigns which looked at kind of in situ measurements of dust, and they found more coarse particles than expected. All of them did. And so this plot here on the right shows 2 size distributions from the salt trace campaigns, which took place here and over in the Caribbean. And they found that actually there were more coarse particles than they expected in the Caribbean. This dashed line here is about 7 microns diameter. And you shouldn't really be getting particles more than 7 microns diameter at the Caribbean. They should have dropped out. They're too heavy, they're too big. However, you can see that there were these particles, so in this red line here, there were particles more than 7 microns making it all the way to the Caribbean. So all of these campaigns kind of proved that there were more coarse particles than we expected, which is still a little bit unexplainable because we don't really know how they're getting there. Based on gravitational settling, they just shouldn't. It's like at the start of Bee Movie, I think they're talking about how bees just physically shouldn't be able to fly because their bodies are so big in comparison to the size of their wings. It's like that, they shouldn't be making it that far. I think there were also some sediment traps in the middle of the Atlantic, and they found coarse particles as well. And they were traveling, I think, more than 3,000 kilometers further than they should, even in kind of like peak summer windy conditions. Next, please. So hopefully that gives you a bit of an idea of kind of the motivation behind my projects and why we care about these coarse particles and why we need to try and understand them a bit better. So this is kind of the main aim of my project, is how are these coarse particles traveling so far from the Sahara? Why? So these 2 points here are kind of the first stages in my PhD, and hopefully what I've managed to kind of get done up until this point. So first of all, just thinking about the observations that I have. Actually, wait, could you go back a step? Yeah, so basically I'm using these observations in my kind of project to try and look at how the size distribution changes from kind of source and then downstream across the Caribbean. So yeah, trying to look at those observations and work out kind of how that size distribution evolves over long range transport. So kind of how important are the giant particles? Are they sticking around for the entire journey, which we know they are, but maybe how fast are they kind of dropping off? And then, you know, are they remaining mixed within the Saharan air layer? That's what SAL is the Saharan air layer. You get this big, dry, dusty bit of air coming off the Sahara, and that kind of travels all the way to the Caribbean. So really trying to think about those coarse particles in terms of those observations, and then using the Met Office model to try and simulate that evolution to see how well it does. Can it do, you know, the height of transport, the size of the particles, and also the length of the transport? So is it able to match these things that I've looked at there? So, in terms of the methods, so this is a bit about the aircraft campaigns. So as I mentioned, I've got those 3 campaigns. So there was Fennec, which was at the Sahara and the Canaries, Salt Trace, which was Cape Verde and Caribbean, and then AirD as well, which was at Cape Verde. I think at this point, it's something that we're thinking about, but basically, because AirD was in August as opposed to the others being in June, this might cause some slight ripples, I suppose, in my results, which we're still thinking about, and you'll see those in a bit. So I thought I'd just point that out now. So basically, what these campaigns give us is these vertically resolved size distributions. So how they do that is they've got these planes. So they use the FAM aircraft for Fennec and AirD, and then the DLR for Salt Trace. And they have these little instruments on them, so you can see them just under the wing there. Or that's some of them, some more they have in the cabin. And they basically fly quite low and then just go up through the atmosphere up to about 8 kilometers and then back down again. And you get these really nice profiles of the size distribution throughout the atmosphere, or throughout the bit of the atmosphere that we're interested in. And basically to do that, they have to use multiple different instruments, because measuring between, you know, 0.01 microns and 300 microns, you need to measure them quite differently. So they have quite a few different instruments on here. And yeah, the FAM was actually quite unique in that it measured up to about 300 microns, which is quite a bit larger than a lot of previous campaigns had done. I think while the coarse particles were kind of considered a bit more negligible, a lot of campaigns maybe only measured up to 20 microns. So then this was quite kind of, I guess, novel in the fact that it measured up so high. Please. So then, as I said, I'm comparing a model simulation to the observations. So I'm using a MET-UM HADGEM 3 atmosphere only simulation. I don't know how much that means to some people. It's basically just a version of the Met Office model. And I'm using the old scheme because currently the new scheme is not up to scratch yet on dust. I think all of the aerosols in the MET-UM at the minute use the new scheme. Dust didn't quite work out in that, so they're still using the old classic scheme, which has these 6 size bins, which are up here, which go all the way from 0.06 microns up to 63 microns. Again, that's nice and novel because a lot of climate models tend to maybe only model up to 10 or 20 microns diameter of those dust particles, just because that larger size bin, so bin 6, 20 to 63 microns, it's quite computationally expensive and was, up until about a decade ago, kind of assumed fairly negligible in terms of we just didn't think those particles were there, so why would we model them that much? So then this is my simulation basically. So this is the AOD, which is aerosol optical depth. It's basically just how much dust you've got in there and kind of the optical properties of it. So you can see it's quite high over the Sahara. And this is the campaign in those kind of green lines there. Yeah, you can see that it models this plume that goes all the way to the Caribbean. So these grey boxes, so if I say the model says this at the Caribbean, that's basically everything in that grey box averaged. And yeah, got five model dunes at the minute, which is why I mentioned the AIR-D was in August, because we're not entirely sure yet what kind of implications that has. It's something I'm going to be looking into, because the AIR-D campaign, which was the one that was in August, is a little bit different. Next slide, please. So, try and kind of set some expectations for what we get from my results. So this is kind of what I've looked at so far. I'll come back to these questions after I've shown you my results, and hopefully we can just get some vague, brief answers to these. So, is the amount of dust in the model high enough? Is it getting the magnitude of that dust right? Then does it get the vertical profile right? So the total profile, is it getting the shape of it, the amount of it? And then is it managing to get the right size particles in the right place? And then finally, again, I suppose that's the same similar thing. Is it getting the right size particles in the right place, but horizontally? Is it getting them all the way to the Caribbean? That kind of thing. So first thing that we looked at was this thing called the aerosol optical depth. And so what we've got at the top here is satellite observations. It's a 20-year June mean. And then at the bottom, I've got the 5-year modeled mean, which I showed you on the previous slide. So I think spatially, it's not doing too bad of a job. In terms of the actual kind of numbers, the model is maybe only getting up to 0.3 in terms of AOD in the middle of the Sahara, whereas the observations are going much higher to maybe 0.6 or 0.8. So that's suggesting that the model is maybe struggling to get the right level of AOD. It's getting it by about half. And this is likely just down to how they've tuned the model. So with the tuning, they tend to try and just match things like the AOD, and they've obviously, this one's just been tuned to about kind of half of the level of this. So next, please. So as I say, they've tuned it to get the AOD right, and then what happens is that you actually struggle a lot in other areas. So this is the vertical structure of the total dust mass. So starting from the left, we've got the Sahara, Canaries, 2 Cape Verdes with the 2 different campaigns, and then the Caribbean. So solid lines, observations, dashed line, model. And you can see maybe it's struggling. Basically, all these lines are nearly flush with the 0 line. So while the The AOD is maybe the model's kind of underestimating by half. This is more like a factor of 10 below the observations. So click watts, please, thank you. So I think it's also kind of interesting to note as well, alongside the fact that it might be quite difficult to compare your observations and your model, it can also be difficult to compare between your observations. So, for example, this peaks at about 800 micrograms per meter cubed. This campaign, you know, it's going up to about 2000 micrograms per meter cubed because they were in different years under different conditions. The Salt Trace campaign measures quite a heavy event with a lot of dust. And so that brings us to why we normalize. So I thought I'd introduce this now because it comes back again later. So yeah, the reason we need to normalize is to be able to compare between those campaigns, and then also to be able to make it a bit more difficult to compare between observations and model. So this is what it looks like when it's normalized. Much easier to look at. So you can actually now, so basically we lose any value of the actual concentration, but we can now see that the normalized mass concentration, we can compare the shape of the profile from the model and the observations. And I was very excited when I did this the other week because you can see, for example, in the Air D Cape Verde ones, this middle green, let's get my word. You can see that actually the model in this dashed line is kind of struggling to get the peak concentration and then also trying to get the minimum. And it's the same at the Sahara and at the Canaries as well. So closer to the source, it was actually struggling a bit more to try and get that profile right. But then when you get to the Caribbean, it's doing a wonderful job. It's really matching that shape so well, and even gets down to very low concentrations up there. I was very excited about that. So while it's struggling in terms of the actual absolute values, when you normalize it, the model's not doing too bad of a job in terms of the shape of that total profile. So then these are complex plots. So I've done a nice bit of kind of explaining. So now we know what the total dust profile looks like between 0.06 and 63 microns. We're going to look by size bin. So click once, please. So first of all, these black lines on each plot, they are the mass concentration profiles, which were the same as what we were looking at on the previous plot. Next, please. The colours are representative of those size bins. So basically red being the smallest size bin. So these are the size bins from the model that were in the table up there. And then purple is the largest particles, so between 20 and 63 microns. Click again, please. Thank you. And then these have just been broken down. So I've split the data up into those 6 bins, and then we're looking at the percentage that each of those size bins, the amount of mass in each of those size bins, what that contributes to the total mass. So this line here, what kind of each bin contributes at each level of altitude. And so the more wiggly ones, there are observations, then the smoother ones are our model. So on the left, we've got the Sahara. Please. And again, thank you. So yeah, over here we have the Sahara. Yeah, that is the left. Sorry, all of a sudden I was like, wait, is that the right again? And you can see that actually in the model, where it's maybe saying that, so these 2 bins, the blue and the purple, between 6 and 63 microns, the model's maybe saying, you know, at this altitude here at 2 kilometers, it's contributing about 40% to the total mass. Observations is closer to 90% of the total mass is coming from those 2 bins. So you can see how actually the model is really overestimating the importance of those finer particles. And then again, at the Canaries, it's a very similar story, except now the model is really, really struggling to represent those purple particles. Those largest particles, there's only a little slither of them in kind of the bottom kilometer. And that's just as soon as you get off the coast of Africa, all of these coarse particles just drop. They just all seem to drop out, but that's clearly not what we're seeing in the observations. So then again, going a bit further downstream, we get to Cape Verde. So this is data from the Air D campaign. And you can see, again, the model is really struggling with those purple particles. It's also starting to struggle a bit more with the blue. It's maybe only representing kind of, actually, could you click again? I have arrows for this, there we go. It's only representing 22-ish% of mass is by those blue and purple particles. And here it's, you know, more than 50% is still from those coarse particles. Click, please, thank you. By the time you get to the Caribbean, it's abysmal. Purple's entirely gone. Blue is, what, about 5% of the mass? And observations, no, it's still more than 60%. So you can really see how much the model is just dropping those coarse particles so quickly and then just completely overestimating the kind of the mass of those fine particles. So we come back to the normalization again in a minute. So these are my volume size distributions. So we've got the volume distribution up on the y-axis and then diameter across the x-axis. So this is basically just the amount of volume per size bin. And this has been split up into, the size distribution basically just shows those 6 size bins. So there's just 6 points along here. And we've only got from the Sahara to Cape Verde because Salt Trace data is not currently playing ball. But I do have like preliminary results, which I will mention. So if we could click, please. So what we're going to do is we nicely normalize these plots again, and it makes it quite a bit easier to try and understand what's happening. So in these first 2 plots on the left, you can see that the model, which is this dashed line, is peaking in bin 4, which is earlier than where the observations are peaking in bin 5. So again, that kind of just proves that the model is just shifting basically all of where it thinks its mass and its volume is shifting it to smaller sizes. And I think, yeah, so first of all, it's got the peak in the wrong place. Next thing to note is this gap between the observations and the model in bin 6, so at those largest size ranges. What my issue is here is that there's already, you know, the size distribution at the Sahara is already wrong. And that's close to the source where, you know, there shouldn't have been too much deposition already, which suggests that the emissions aren't quite right. So it's already underestimating. So this drop here between bin 5 and bin 6 is already overestimated in the model. As you go downstream, that difference between those, the observations and the model, that difference begins to increase. I'm just going to ignore this one on the right for a second. So basically, through the preliminary results from the Salt Trace data, which is at the Cape Verde and Caribbean, this gap just continues to increase. This kind of, you know, bin 6 points are going way down here. It's completely, yeah, as we saw on the previous slides, it's completely missing those coarse particles. And so what that's kind of telling me is that there's a problem at emission, but then there's also this swift deposition of the coarse particles, which just means you're increasing that kind of magnitude of underestimation in the coarse size range. The reason I ignored this one is because this is from the AIR-D campaign, which was the awkward one in August. And what you can see is that it's almost a better fit. It peaks in bin 4. It has a bit of a drop off to bin 5, and then again, it still struggles a lot with bin 6. But yeah, this is something that we're going to have to figure out, whether it might be because that we've only got modelled dunes. I don't think we're really expecting the size distribution to be that different in August, in modelled August, but I guess we'll find out, because who knows, it might actually match up a bit better, or it might be completely different again. Guess we'll have to wait and see. So next, please. Okay, so back to these questions. Is the amount of dust in the model high enough? No. It's probably down to tuning. So in terms of the AOD, it's not doing too bad of a job in comparison to how it's doing with the mass and the volume, which is completely underestimating by like factor of 10, whereas AOD was maybe only a factor of a half. So yeah, even if a lot of these models tend to get the AOD right, they're still really underestimating the kind of the amount of dust there. is it doing the vertical profile any justice? It represents the relative total vertical dust profile, but not the vertical distribution of the varying size particles. So it's got the total profile, it's got the more kind of in the right location. That's what we saw by those normalized profiles. It was getting the, I guess, yeah, the distribution vertically of that dust in the right place. But then from the next plots that we saw, it's not getting the right size particles. And then again, is it capturing the size distribution evolution? Not really. It's overestimating that deposition of the coarse particles, which really means that there's a big magnitude or a growing magnitude of difference the further downstream you get from the Sahara. So far. So observations show that the coarse particles are not deposited as quickly as we expected, which fun. Because why they're doing that, still not sure. As I say about the bees, they just shouldn't be going that far. And then after long range transport, we've got a mass underestimation in the model due to low emissions and fast deposition. So in my project, I'm basically aiming to just look at transport and deposition. The emissions problem, there's other people working on that. But so we know that's an issue, but then that kind of increasing magnitude of difference says that we've got this fast deposition rate as well. So what is next? Click please. So the first thing that I'm so now that we know that the model is really struggling, the next kind of phase in my PhD is to try and work out maybe why. So I'm going to start looking at which processes in the model might be dominantly controlling the size distribution. Is there something that's overactive? Is something not active enough? What's going wrong that means there's that really swift deposition? Next, please. And then, are there processes which are not included in the model? So there's been a lot of kind of speculation about different mechanisms, which actually, if we go on to the next slide, please. A lot of speculation about different mechanisms which could be increasing that kind of lifetime of the coarse particles in the atmosphere. So there's our understanding in the middle, and we're saying, but based on like everything we know, the particles should be doing this. The model is over here getting it completely wrong and just saying, well, they're not really doing any of that. And then over here is what the particles are actually doing. And we don't understand either of these. We don't know why that's doing that or why they're going so far. So I'm trying to work that out. So there's things like triboelectrification, where the particles bounce into each other and give each other an electrical charge. And then having that charge can hold them up higher in the atmosphere for longer. So, if something's higher up, it's going to take longer to come down again, could increase the lifetime. And as I mentioned briefly in the introduction, having a different size particle can change the value of that charge. So it could be increasing the coarse particle lifetime. Things like non-sphericity of particles. So I think all climate models represent dust as perfect spheres, and they're really not. They might be something more like this, and you can imagine that might fall in a very different way to a sphere. So again, I think there's been some research that said kind of including non-sphericity of particles could increase lifetime by 20%, which is impressive, but not enough to get it all the way to the Caribbean. And that's basically the same story with any of these mechanisms, is that it could do a bit of increasing, but not enough to the extent that we're seeing. So we're expecting that actually it might be a combination of these things, or it's something that we're just missing entirely. And so then this in the middle is what I'm just going to talk a little bit more about. So this is kind of in the daytime. That's what this lovely little yellow circle is. That is the sun. In the daytime, you've got all of your coarse and all of your fine particles entirely mixed up throughout the Saharan air layer. There's not really any kind of separation. Everything's just really well mixed. And then when you get to nighttime, I was very proud of this as two circles together. When you get to nighttime, the fine particles, they've got no trouble staying up there. They're very fine, they float almost. Whereas the coarse particles, they start to deposit more quickly. And so then you kind of get this lowering of that coarse mass in the atmosphere, and then daytime again, they all mix back up. So it's like it gets, so close to the surface, and then the day comes and it gets mixed back up. And that can kind of just, if you imagine your particles starting over here, it gets up and it's night, and then it goes, and it basically gets all the way to the Caribbean by just this constant remixing during the day. Next, please. So that's why I was in Cape Verde in June. So we were doing this campaign called the Dazzle campaign. I was told it's pronounced Dazzle, which, is sparkly, it's fun. So we were looking at this diurnal cycling, and this is maybe a slightly more detailed diagram of what we were trying to look at. So during the day, you've got these mixed particles, and then the coarse ones start to drop. Day comes back, they all get mixed back up. So what we were doing was we had these drones here from USRL, which is the Unmanned Systems Research Laboratory. And what we were trying to do was basically send these drones up with these particle counters on, send them up just before sunset, try and capture that full, like what the size distribution looks like when it's completely mixed, and then try again when it's just before sunrise, when it's maybe got this kind of slight drop. It would be very cool if it showed that. Unfortunately, it's too early for the results to be kind of fully analysed yet. So that's this is hypothetically what we'd be hoping to see. Whether or not we do is a whole different thing. And I'll have to come back to that at some point, but these are kind of possibly one of the ways that you might be able to measure something like this and prove that one of those mechanisms might be impacting the lifetime of the dust. So back to my conclusions. Okay. Thank you. I like having this stick. So I thank you for your attention, and I will now take any questions if you have them. Any questions?
You said there's various different processes that could be affected.
Yeah.
Surely several of those you could have measured on the aircraft, things like charging, turbulence rates, and so on. Have you not got any data on those aspects?
I don't think so. I'd have to check, so I'm not entirely sure, but I have a feeling. Yeah, to be honest, I'm not sure. I think the majority of the data that I've seen so far is just the size of the particles, temperature, relative humidity. I don't think they were measuring things like charging. But I'd have to check.
I'd be surprised if it wasn't measuring turbulence, because that's a pretty fundamental process.
Yeah, I guess the issue would be, so say if this is the Sahara's over here, you've got the Caribbean all the way over there. If you're measuring here, I guess you're only measuring what's happening there, whereas it could have been that there was loads of turbulence in the middle of the Atlantic that then changed the kind of that vertical size distribution. So then by the time you get here, you're not necessarily measuring. Yeah, I guess you need to be measuring the entire kind of length of that transport to see what's happening at every single stage, as opposed to just what's happening at that one single place where it was measured.
Yeah, no, you're right. That's a fair point. But I was more thinking of the emission, because over the Sahara, the turbulence, certainly by daytime, is often pretty severe.
Yeah.
And that could account for how you get larger particles up and might help with some of your emission gaps. It doesn't necessarily follow further down, but as you pointed out yourself, if there's more going into the atmosphere and staying in at emission, you're going to have more left at the other end of the track.
Yeah, I think, yes, emissions isn't my kind of speciality. I see exactly what you're saying. I think what I'm focusing my attention on is maybe looking at the fact that obviously there was that gap in the kind of the observations and the model at the Sahara, but then the fact that that just kept growing rather than all just reducing at the same rate. I think that's kind of what I'm trying to capture, which I guess wouldn't be. But yeah, no, I see exactly what you're saying.
It might be worth asking. Maybe it just isn't in the data set that you've got, and it exists, but perhaps it wasn't thought relevant. Something. Might be worth asking a question.
Yeah, no, I think I will check with my supervisor because she was on a couple of the campaigns that we're looking at. So it'll be, yeah.
We have a question online from Roll. How will dust in the atmosphere change from climate change? Will it increase the risk or the negative effects, and how? Can I get that sentence out?
Yeah, nobody's particularly sure how dust is going to change with climate change. So I can't give a confident answer. I think one of the things I can say, so in my master's, I was looking at a high latitude dust source. So I think when people think of dust sources, we do often think of places like the Sahara, where it's really dry and, you know, a desert. But this source I was looking at was in Alaska, and it was actually, it was basically where the glacier was kind of producing all of this really fine glacial powder that was getting washed down the river and then kind of settled. And then when the river levels dropped at the end of summer, then you've got all this really fine sediment that gets blown up. And so I think it's maybe a bit easier to work out how they're going to change, because we can maybe see that there's not going to be as much glacial flour produced, or, you know, the melting's going to increase. So it's easier to tell with those. But in terms of places like the Sahara, I'm not really sure. I'm trying to think of some of the specific impacts. But yeah, no, I can't think of anything. I'm not sure. I'm sorry about that.
Okay, I mean, I could ask 20 questions, but I think I'll just ask a couple.
Okay.
With the dust itself, okay, are you sure you know what the dust is? In other words, the dust from the Sahara, is it the same as what it is in the Caribbean? In other words, composition.
Yeah.
Okay. And you're sure that it's being transported across the Atlantic?
Yeah, so they've done, when they were doing the campaigns, they did some compositional analysis on what they were measuring.
Right.
And so, for example, at the Sahara, Canaries and Cape Verde, they confirmed that everything that I'm looking at is dust. I think in maybe the bottom kind of 500 meters kilometer, it sometimes was a bit more mixed, especially at the Canaries, where you've got more pollution coming down from kind of the Iberian Peninsula. And then I think as well above about 6 kilometers, it was less dust, because that's basically where the top of that Saharan air layer kind of, you've just got these really tight inversions that keep all the dust in and then everything else out. But by the time you get to the Caribbean, it is a bit more mixed. And this is something that we've thought about, which is why I think a lot of some of the data which I've been looking at from the Caribbean, I've only been looking between 2 and 4 kilometers, because we're kind of fairly confident that that is dust. Anything outside of that is started getting mixed in, but the middle, we're fairly confident it's dust. So there is the potential for contamination, but I think what we found as well is it's kind of obvious-ish when there's a fair amount of contamination, because a lot of other particles might be quite a different size. So when I was looking at, what I was looking at a lot in this presentation was the mass and the volume. When you look at the number of particles, you could see at the Caribbean above 5 kilometers, it didn't really, the number of particles didn't really drop off. It just kept going straight up, because there were all of these really, really fine particles that were pollution or something else that were basically kind of mixing in. Yeah.
So if you've got the contaminated particles in the dust as well, that's going to affect the charge status of that dust cloud at various points.
Yeah.
And that's going to affect deposition rates, it's going to affect mixing. And also, if you've got coastal effects, that's going to affect the cloud as well. Onshore winds, offshore wind, time of day. If the aircraft took the measurements on a particular day and got a set of results, and it took them 5 hours before or after or next day, would you get the same profile?
Probably not.
Exactly.
Yeah.
So I think you've got a lot going on there to give you confidence between the observations and the model.
Yes. Yeah, so I think with the field campaigns, it's usually about over a 10-day period, and we might have 20 profiles that feed into that, which compared to the model, I was comparing, 5 Junes, 5 months, whereas, obviously if I'm comparing that to 10 days. And so I've done a bit of work to try and look at, I haven't necessarily looked at, I guess, the kind of what specific impacts might change the profile, but I did have a bit of a look at, so if you've got a high AOD event and a low AOD event, how different is the kind of the contribution by bin to total? How different is that between each size bin? And to be honest, there wasn't too much difference. So I've at least got a little bit of confidence that when you've got a high event, like a high dust event and a low dust event, that they're kind of, hopefully that shouldn't impact what I'm looking at too much. But I do appreciate that there's other factors which can impact it. And I mean, that's kind of the thing as well with the AirD campaign, because it's completely different to any of the others in terms of that size distribution. So there's something at play there that we don't really know about yet. So it's going to take a bit more investigating, and I guess that could kind of turn up other things as well as to what might be changing it.
So I just wanted to end it on two comments, if I may. And the first one was you've got large scale snapshot tests, set tests, and it's quite difficult, in my view, to make confident predictions based on what you've done so far. Of great conclusions, and the forward work plan is fantastic. And but I think with the turbulence as well that you mentioned, that's quite variable, isn't it? With time and over seasons as well, month to month. I would also suggest you have a look at aerosol modelling. Some papers on aerosol modelling, which I've had to do in my past, and that's very beneficial. There's a whole host of technology out there on aerosol.
Thank you for the comments. No, I appreciate that.
Thank you.
Thank you.
I have questions. So you mentioned there's one model of observation that has 300 micrometers. Are you going to use that? I know you're just using the sizes to compare to the middle of this, but do you think you'll analyze that data?
So I think when I first started looking at the data, we did look at I did look at those particles, which I guess were between 63 and 300 microns. And there was, I guess, I'm trying to think back to it was a year and a half ago. I did look at them, and I think in the end we decided that for this first section of work where I'm just comparing to the model, it was easier to look at when it didn't include that. I basically had them coloured pink. So in my head, they're always just the pink particles. So we decided not to include those pink particles just because it made it a bit more complicated to look at in the context of this. However, I do think it's something I want to come back to, because I can say, well, the model's missing 60% of these particles, but obviously that's, smaller than the actual number, including those particles larger than 63 microns. So I think it's something that I want to come back to.
Amazing. Do you have any more questions? Okay, Blair?
So for the aircraft particle sensors, do you know how they recorded the size of the particles? Did they return any information about the shape?
I think so. Their optical particle counters, I think they're light scattering. I think they basically record the shadow caused by the particle in front of light. And so I do think there is a value which basically it's almost like a ratio value between like the height and the width. So there is some data there on the kind of the level of asphericity.
So could you sort of look at that as like distance that the dust has travelled, and that aspect ratio has changed significantly?
Yes. That is a yes. Yeah, I think, yeah, at the minute I don't have my hands on the data, but I think, I mean, yeah, as I say, Claire has all of the data somewhere in her deep data files. So I think I can try and get that kind of thing off her and have a look at it, because it would be interesting. Yeah, thank you. Yes.
Maybe I missed this at the start, but like, what's the significance of the month like June? Is it something when there's the most?
Yeah, so June is basically 2 out of the 3 campaigns were in June.
Yeah, like why?
Yeah, so basically summer is when you get the most dust coming off the Sahara.
So like the African East League.
Yeah, so it's kind of to do with the position of the ITCZ as well. So I think in our summer it's further north. It basically sits right over the Sahara, and so you get a lot of dust coming off that. And then later in the year it's going further south, and so you get less uplift. So I think June, July are very favourable months for observations, and then.
But then you also have the African East League in August.
Yeah. So I mean, yeah. So the AirD campaign was in August, and I don't think we thought it was going to make that much of a difference to begin with, and then it does seem that the size distributions from that are completely different to the other campaigns, which were in June. It's going to take a bit of investigating, I think, to understand why it's so different, because yeah, we were just expecting the entire summer to kind of be fairly uniform in its output, because I think one of the next things I'm doing as well with the model, so at the minute I do just have that June mean, which just matches basically those 2 campaigns. I'm gonna look at an August mean, a July mean, and then also just a summer mean, so all 3 of those months, just to try and understand what's changing and if it's a significant difference, because at the minute June was basically just the first month of summer for the model, so it was the easiest for me to run.
I get like the weather conditions in June and August might be a bit different. Like maybe the jet's a bit stronger in August, and maybe it's like tropical cyclone season, so like there's more moisture.
Yeah, I think it's something that needs exploring a bit more into how that kind of impacts, I guess, what I'm looking at. But yeah, thank you. Yeah, that's a good point. Yeah.
Can I make a comment rather than a question? It's easy to think of the Sahara as a contiguous mass of sand, but it's anything but. And there are very different source regions, and they also vary by season, by month. And you might find that your August dust is coming from a different source completely. I mean, it's a very big place.
Yeah, I think that, so there's been some, when these campaigns first happened, there were a few papers that were kind of published that had like back trajectories and that kind of thing to look at source data. So I think I need to dig into that a bit more as well, because I do understand obviously, yeah, the kind of the source region can really impact that size distribution, as well as maybe how far it's had to travel to actually get to the point of being my version of the Sahara. So yeah, there's that uncertainty.
It's worth checking, because you can get a lot of dust from certain areas where the dust just happens to be fine, like dried up lake beds particularly.
Yeah.
And in other areas where it's more rock debris basically, and it's a bit sharper and it's a little bit larger, and that might advise results.
Yeah, I absolutely wouldn't be surprised if the AirD data did come from an entirely different section, because that could very easily explain what's going on. So yeah, it's something that I think it'd be a good idea to look into. Yeah. Any more, Charlie?
So I'm just piggybacking on what other people just said. You were looking at means, you said, in the model for like June, is that right?
June mean, yeah.
So maybe if you looked at, maybe not the mean, but like standard deviation or something, you might see events like the August case, they might actually happen in June as well.
Yeah.
I'm just wondering whether, because you're taking a mean, you might be missing out those June events. Like, do you know how variable they might be?
Yeah, so this is something, can I just flip back a few slides? So, okay. Oh, I'm looking for that. this. Okay, this is something that we've thought about and that I'm going to be looking into over the next couple of months, because what I was saying about how these model lines are so smoothed out, I'm going to start looking at a couple of weeks of individual daily profiles and see how variable they are compared to that mean. Because yeah, I'm taking a large mean, it could be. So that is something that we're going to look at, I think. Yeah, thank you. Yeah.
So, sorry.
You're right.
So here when you're comparing the normalized mass concentrations as opposed to the absolute values, if you've not got that much confidence in the absolute values that I've got as it's getting wrong values, how can you have the confidence in the shape of the profile of the normalized values?
This is so. Okay, yeah, so in terms of the observations, I know this seems like I'm taking a complete, in terms of the observations, yeah, so I was saying I've looked at kind of high AOD events and low AOD events, and it didn't particularly change, oh no, sorry. Sorry. So between high and low AOD events in the observations, these kind of percentage contributions didn't particularly change. So for a while, I've been kind of running on the assumption that it's going to be the same story in the model. It's something that I need to check, but basically, what was the question? Sorry.
If you've not got confidence in the absolute values, why do you have confidence in the normalized values?
Okay, so basically, even if the model is only representing this much dust, the hope is that these types of things would still be the same. So the actual like size distribution within that, whether it's a big event or a small event, or whether it's not showing much at all, i.e. a small event, hopefully it's not going to change too much how these things look vertically and how each bin contributes to the total. So then back. So then we hope that actually that profile wouldn't change much either, or the shape of it, because it's all just still in the same position. But yeah, yeah, I hope that answers your question.
Thanks.
I've just thought of something for you.
Okay, perfect.
You've got a large data set here. Large sets of data.
From model or observations?
Well,
Both.
both. Okay. So what you could do is apply some statistics. Not just any old statistics, but significance testing. And you could also sample the data. So you could take several samples from each data set.
Yeah.
And compare, you know, mean, maximum, minimum, standard error, all that good stuff.
Yeah.
And you can sample from location to location. And then you could do some significance testing on that.
Yes.
There's a lot of work there. But it might, as well as the aerosol modeling I mentioned.
Yeah.
We've got another 3 years work.
Oh God.
But I think some of the answers to your question are in there, but you just need to dig into it a lot.
Yeah.
Because and that will give you the confidence long term.
Yeah. Yeah, I think I've been kind of, over the last month, I've been playing around a lot with kind of, where am I getting my confidence from? And yeah, it takes its time, doesn't it? But it's worth it, yeah.
It is worth it.
Yeah, just to prove that this actually is a solid kind of conclusion.
So rather than looking at the big picture and trying to make broad conclusions, you can sample small pieces.
Yeah.
And try and build some answers up.
Yeah, I think even yesterday I was talking with my supervisor and we were saying that I should look within each box, look at all the different locations and try and get an understanding of that variability. Yeah.
And the excitement builds after that.
Yes.
Okay, we'll wrap up. Thank you very much, Natalie. January, and there'll be talks on heat waves. More information will be coming soon.